Hello, welcome to ICS Virtual Coder Video. Innovative Coding Solution, abbreviated ICS, is a company specializing in PVD coatings. ICS develops custom processes and coatings, and helps its customers implement the solutions in their own facilities. ICS also offers film growth simulation services, and sells in-house developed ICS Virtual Coder software. ICS Virtual Coder is a software suite that simulates the growth of a PVD deposited film. Depending on the characteristics of the deposition machine and deposition conditions, this easy-to-use simulation tool enables you to evaluate coating properties, find the key parameters affecting the physicochemical properties of the coating, improve the deposition process. In a previous video, we explained that simulations using ICS Virtual Coder involve several steps. 1. Defining the process and motion of a representative sample. You specify the source and motion characteristics like singe or two-fold rotations. You use make process for this purpose. 2. Launching the film growth simulation by using the NASCAM simulation algorithm. 3. Evaluate the film properties. There are two types of film properties, the one that can be computed on the fly like the chemical composition versus depth, which are called basic properties, and others that are the properties evaluated once the film is completed like porosity, mechanical or optical properties. For this tutorial, we'll start with the configuration of 4 vertically positioned rectangular magnetron sources. These are called S1, S2, S3, and S4. Each source is metallic, and their fluxes are identical. The process takes place at constant pressure. A representative sample, whose initial position is indicated by an arrow, is given a two-fold rotation. Once the configuration and process have been described, we'll run the film growth simulation and analyze the basic properties of the film. On the left, you'll see a description of the 4 sources, and on the right, their graphic representation. The first magnetron source is a zirconium source. The second is chromium. The third titanium, and the last aluminium. The process takes place at 0.5 Pascal. The motion of a representative sample is defined here. We can see that it is the superposition of 2 simple rotational movements. Once the process has been defined, the Virtual Coder Make Process plugin calculates the flows of all the species, along with their respective energy and angular distribution as they land on the sample surface. Remember that the process takes 2 minutes, divided into 33 sub-steps. Now that all the angular and energy distributions of the condensing atoms have been generated, we can load them into the film growth simulation module by pressing the Generate Project button. We now close the Make Process plugin. Looking at the film growth simulation parameters, we now see that the growth is divided into 33 layers. Let's run the film growth simulation. For that purpose, click on the top right green button. The monitor window shows which of the 33 layers is currently being deposited. Once the 33rd layer has been applied, we can analyze some basic film properties. Let's start by visualizing the film in 3 dimensions. Virtual Coder allows us to visualize the 3D structure and orient it in all directions. By pointing at the atoms represented by different colors, we can determine their nature. It is also possible to analyze the basic properties of the deposited film directly in the Virtual Coder GUI, using graphs showing the evolution of certain properties as a function of deposition time or thickness. For example, Here we draw the chemical composition of the film as a function of depth. The substrate is on the left, the surface on the right. The x-axis shown here is the number of the atomic layer deposited. We have therefore deposited a fairly thin film, 65 monolayers thick, around 13 nanometers. Obviously, extending the process time or the deposition speed in Make Process plugin will increase the film thickness. Let's now analyze the evolution of the chemical composition of the elements present in the film. For that, we replot the depth profile like here. We have here in green zirconium, in yellow chromium, in blue titanium, and in red aluminium. In order to understand this complicated profile, it is useful to go back to Make Process and see the different flows involved in film growth depending on the position of the sample. As a reminder, the order of the cathodes was zirconium, chromium, titanium, aluminium. Also, the side on which the sample receives flow is symbolized by a green arrow. In step 1, the sample is in front of the zirconium cathode. In step 2, it receives flux from the chromium and titanium cathodes. In step 3, it receives flux from the zirconium cathode, and reduced flux from the aluminum cathode. In step 4, it receives flux mainly from the chromium cathode. It's the same situation in step 6, where it receives flux mainly from the chromium cathode. In step 9, it receives flux from the titanium cathode only. The same situation occurs in step 26, where it receives titanium only. In a nutshell, the sample is first bombarded with zirconium. Then, for the next 3 or 4 positions, it receives mainly chromium. Then, it receives a lot of titanium at steps 9 and 26. For the last few seconds of deposition, it receives aluminum. Finally, between the 2 titanium flows, it receives a mixture of all the elements from the other cathodes. To sum up, the calculation of different fluxes from different cathodes as a function of sample position, combined with the calculation of scattering of species in the gas phase, which modulates the energy and angular distribution of atoms condensing on the sample, explains this complicated concentration profile. Prediction of this complex concentration profile can only be made using sophisticated simulation methods such as those integrated into the ICS Virtual Coder. The film growth simulation and basic properties analysis are now complete. It's time to analyze its advanced properties. We'll see how in another video posted on the same website. Thank you for watching.